Hello, everyone, and welcome back to the VMware Networking and Security live stream. This is the place where we talk about networking, security, and how it all relates to NSX and what we do on a daily basis here. So we bring on product experts, we bring on subject matter experts, and today we're back to talking about networking, one of my favorite subjects of all time. We've been doing it for the previous weeks, and now we're just going to keep on continuing, and I was thinking we're going to go a little bit more in depth on the edges, and I'll tell you why. So first off, let me bring in my guest. He's back for, I believe, the third week in a row. His name is Mr. Paul Mancuso. How you doing?
Thanks, Andrew. I appreciate that. Sounds great to be back here. Coming back so often, maybe we have to start making a little bit of somehow a banter about what we're going to be able to provide between one another as far as coming back so often on these telecasts. I love doing this. This stuff's great.
Oh, it's a lot of fun. And I noticed that you're drinking green tea, and as am I, although you drew it out. I just have it here, the world-famous green tea.
Well, I have to get good at my artwork and have to take a lot of advantage of the colorful means of artistry I have.
Yes, I like it. So, Paul, it's funny. So what I was doing was, like everybody I'm sure that's watching right now in the live stream, which, by the way, before I continue, just remember, we welcome questions. So if you have a question, be sure, I always have it up on the screen here. I'm taking a look at it, and we're going to answer your questions live. But on to the topic of today. It's Edge Day. And yeah, so what I was doing, because I believe that all of our viewers do this as well, I was reading through the design guide here, and I was on the 4.9 section about the Edge node. And man, did I find a lot of good stuff. I started highlighting different areas. I started, kind of going through it. I'm like, man, I think we need to have a show that's, I know we talked about it a bit on the previous shows, but let's go all in on the edges. Like, let's just talk about it. And let's talk about some of these cool things that I'm noticing. So for the audience that's out there, what I want to do is I'm going to post up the reference design guide that we're going to be talking about today. So it's up there. If you want to follow along, it is going to be on page 174. Actually starts on 173, section 4.9. We're going to be talking about edge nodes. So how they are, why they are, what they do. So Paul, let's start off with this. We know that an edge node has DRs and SRs and things. We can talk about those components, and the SR components are, talking about, physical infrastructure connectivity like BGP, MPBGP, and OSPF, VRF Lite, EVPN, all that good stuff. But I want to just start off with, there was a section in here that I think it's very important to distinguish here. So highlighted here I have is the edge node is also a transport node, just like ESXi servers. And just like an ESXi server, it can connect to more than one transport zone. Meaning, so we're going to break down the transport zones real quickly. And then on top of that, a specific edge node can only be connected to one overlay transport zone. And depending upon topology, is connected to one or more VLAN transport zones for north-south connectivity. So first off, Paul, let's get a little bit more in depth of the different transport zones. We have overlay transport zone and VLAN back transport zone. Let's talk about those first.
All right. When we draw this out, obviously, since we're still only on a two-dimensional drawing, as nice as it is and clear as we can make it on the light board, it still is two-dimensional. So you'll just have to imagine ideals as we discuss them in your mind as we describe them, I suppose, would be a better way of saying it. So let's do this. We'll draw things in the way we should reference these drawings, at least going forward for today, because vSphere is often referred to as the southbound, with NSX, of course, driving traffic north and south into and out of it, and NSX would be the southbound, the stump network per se, or the stub, I should say, stub network.
I don't know. I like the stump network. I'm a fan of that.
That's right. All right. So we'll use the familiar colors that we'll have. We have vSphere for green. We have our NSX as our purple here. And when we speak about transport zones, then we are speaking about more the ideal of which traffic is east-west and which traffic is north-south. Now, VLAN traffic transport zone technically could be either, because it depends upon the nature of their use. So that's a little difficult, again, to describe them as east-west, north-south, or even to picture them here in a two-dimensional drawing per se. But if we were to draw out what hosts were going to be driving the TEP communication inside of the virtualized network of NSX itself, that would be our east-west, right? So, and again, that virtualized network that we're discussing would obviously be the logical segments versus the VLAN back segments. Although technically VLAN backed as well as logical segments, is still east-west communication inside of the data center. It's just that we can drive and provide the directional value of managing and manipulating that east-west traffic a little better when we do it so within the network virtualized environment. And that's the one we're going to discuss today. So for the purposes of today, we're going to utilize two specific types of transport zones. One that'll be east-west, that'll be our logical segments.
Okay.
All right. And that'll be the transport zone that we'll discuss and describe a little bit more clear in a moment. And then the VLAN back transport zone that we would use for our edge communication, because the VLAN back transport zone here obviously would be referring to the VLAN transit connectivity that we would have for our north-south edge routing adjacencies into the physical fabric switching. So our physical fabric switching would, of course, be up here.
So essentially what we're saying here is the VLAN back transport zones, that's where we're going to be running our BGP or OSPF, are just sending our traffic out into the enterprise network. That's our on-off ramp.
Correct. And we're going to obviously go through a couple of iterations of drawings here, just because some of the topics we're going to do is it's not going to be conducive to have one drawing to go throughout the entirety of the discussion, likely. We might, but I think it's going to end up diverging where we're going to have one that's going to be prescriptive for a specific topic, and then we're going to probably end up having to draw something out a little differently. But nevertheless, we'll have our edge nodes. So we'll have, let's say, our vSphere host, and let's do it this way. Let's try using this one here. I don't know if this is actually going to show up that much different, but this would be, let's say, our, now they show pretty much the same. All right. These would be our vSphere clusters, let's say. So these are our vSphere clusters for NSX. So the NSX vSphere clusters. Okay. NSX vSphere clusters for workloads.
Okay.
All right. And then what we'll do here is we'll draw this in red, the edge. And again, we're just going to do so in a very small format here today for this first initial transport zone topic. And then we'll wipe this out and make it bigger as we talk about the nodes a bit more explicitly. So in this cluster here, these would be our NSX, all right, hosts for edge. And we should probably clarify that in a little bit, but let's do the transport zones first, and then we'll clarify some nomenclature so that when we start going back and forth between clusters, between edge clustering, between edge nodes, we have a firm foundation of what those terms mean, because again, people who are not familiar with using those terms, it becomes a little confusing because we'll say, oh, the edge cluster, and we're referring to the actual virtual machine or bare metal nodes of that, not the vSphere hosts.
That makes sense.
All right, so that's why it's important. So that's why I said the NSX hosting the edge here itself, those would be the vSphere cluster itself. Does that make sense?
Makes a lot of sense.
Okay, all right. Now, when we talk about the transport zone, the problem is that this is where it gets a little sticky here, okay, as far as this goes. We'll have the workload domain transport zone technically has to encompass all of the communication here. So this would be our, let's say, our overlay network zone. Now, notice that I drew it over the workload clusters and the hosts that were hosting the edge virtual machine clusters. And the reason being is that, remember, in order for communication to exist and come in on a north-south perimeter, which we're going to get to in a moment, and then move laterally on an east-west basis, the tunneling endpoints at the edges must communicate in through the distributed routed network of the virtual network overlay of NSX to and from the workload domain.
Yeah, there has to be a way for the edges as the traffic comes in. It needs to also be aware of the TEPs and has to have its own TEPs in order to be able to then transfer it over to the NSX vSphere workloads that then in turn have the VMs.
And in order for that to be, then what we need to understand then is what is part of that transport zone. So in this particular case, the vSphere hosts themselves are the members of the transport zone. In the NSX edge, it can be one of two things. It would either be the bare metal edges themselves, because they're the ones that provide the service of transport services north-south and east-west, right? Or it would be the edge VMs. And notice what I didn't specify. The vSphere hosts that are hosting the edge VMs. They are technically not playing into that role. They're simply the cluster that's hosting the services if we use the virtual machine edge format. Does that make sense then?
Makes
Andrew?
sense. And just to say, like, they can both be unprepped and prepped. So it doesn't matter on the host that the NSX edges are on. There used to be a format, and we talked about this, where you didn't prep those hosts, but nowadays we actually have changed that tune, and we do say that you can also prep those hosts as well.
And that's true. But even though we prepped them and they would technically be part of the transport zone itself or the overlay or the VLAN, because they would obviously have the prep services, which would apply that when we go ahead and then select them to be part of the zone, they just would not likely, again, not likely, because carry workloads that are actually participating in the east-west communication. They're carrying and hosting the virtual machine edges that are doing the work effort. Now, we're going to try and keep it simple, because we could get into some fairly complex design discussions where we would condense the form factor usage. We could use the ESXi host that hosts the edge in a dual nature, or even a tri-nature. We could actually utilize it for the workload, so that for the transport portion of it is hosting virtual machine workloads. And then there's virtual machine edge nodes that are communicating on a north-south, as well as communicating to workloads that are either upon the host themselves that the virtual machine edge nodes exist upon, or they're obviously transmitting distributed routed nature into other hosts within the environment itself, as drawn out here.
And I think it's important. It's important to say along with that is, the reason why there's a lot of design consideration there is because depending on the size of your hosts that you have that are hosting the edge nodes need a certain amount of CPU and they need a certain amount of memory. Not only do they need it for the kernel, essentially, or the control plane functionality of it, but it also needs it for the data path, the fast path interfaces that are there. And depending on the size, that's going to also determine how many CPUs are allocated. So you really want to make sure that you're not overtaxing your ESXi hosts that are hosting your edges, or your VM edges in this case. Would that be a fair point, Paul?
Right. Well, it's a fair point, but the bigger consideration would be more along the line of, in most circumstances, is how many hosts do I wish to dedicate for particular purposes? So I could be a very large customer and only using, in this particular portion of my world, a very explicitly small-sized amount of my hosts for this NSX domain. And in this other NSX domain, it's extremely large, and I would have a different design consideration. Going back to what Andrew stated, performance characteristics, how would I want to scale it out? So therefore, maybe I want to sectionalize the usage of the vSphere hosts themselves for particular purposes. So have a management domain, have a workload domain, and have an edge domain, so that each of them scale completely agnostic to one another. Obviously, the workload domain scaling quite a bit more. The edge clustering would actually scale based upon how many edge nodes I would actually require for their north-south, east-west communication transfers of I/O. So that's why I said we could easily get into some complex design consideration. I just wanted to keep it simple here, and we're going to assume that for the purposes of here, our workload domains, whether or not they're carrying the management, it's irrelevant, and there's going to be edge ESXi clusters or edge hosts that are going to host the virtual machine edge nodes. So that way then we can be very discriminatory about what terms are being applied to what in our conversation going forth today, just to keep everything else out of scope.
I think that makes a lot of sense. A lot of sense.
Yeah. But what we can do, though, to promise the audience, is that we'll have a design discussion that will go back in to say, when should we consider those other characteristics of designing the environment in, maybe a multi-part design discussion, because those become very interesting in obviously consideration of how to scale and how to set those up and for what purposes, et cetera. But again, it doesn't necessarily imply you're a small customer versus a big customer of NSX or a usage of it. It just implies to what NSX workload or domains do you wish to utilize for this particular deployment in this environment for this purpose, etc. Okay. All right, so let's get back to this. We only did the overlay. We only did the overlay so far, so we didn't actually hit the other one. So let's get that one real quick. Now, the VLAN-backed domain is what it sounds like. All of the traffic that would be coming inside of the transport nodes, the virtual machine edge nodes, bare metal, or vSphere hosts, would be backed by VLAN DV port groups, not logical segment DV port groups, or in the cases of an edge VM explicitly, they would be used for the transit connectivity for the routed north-south movement of traffic, so that when traffic comes in through the fabric of the physical switching world, it would route through the edge, your border leafs, or whatever you wish to refer to them in the physical fabric, into the edges. And because that first hop into that edge, into the SR that we're going to talk about a little bit about later on, of our tier 0 routers, would be a VLAN-backed connection. And then the moment it actually begins to be manipulated by the NSX services to communicating it to its destination in the logical network, at that moment, we begin to encapsulate that traffic and use our TEPs, as well as a series of other interactions between the tiering of the routers to communicate that traffic into the NSX environment. I think I'm trying to make that as simple as possible without going through the entire path workflow that we will probably end up doing at some point.
I like to imagine that as, once you get into the edges, it's that magical divide line that once you're in there, you're inside the fabric. So when you're out in that purple area that you have at the very top, that's the enterprise network. And then as you enter in on the VLAN backed interfaces into the edges, and then you have that overlay transport zone that the edges are a part of, now you're magically inside of the NSX fabric. And that's where the segments and the rest of our Geneve tunneling takes over.
Right. So you look at the lines. Obviously, I chose poorly because of the green and the yellow. Again, just looks wonderful. All right. I'll have to do a little better job. I do have more colors here. I could have used orange and red, I suppose. Well, I already did use the red. But anyway, the larger square here sectioned off versus the more elongated pink section here. This one is our overlay transport zone, which encompasses the TEP communication that must exist between all of the transport nodes, inclusive of the edge, and the edge virtual machine nodes. They're technically the transport node. That's something to be aware of. It's not the vSphere host hosting them, although they can be a transport node, as we mentioned before, for other workload servicing if we so desire. All right. So the VLAN connection here is because when we craft our BGP adjacency, so we have our BGP connectivity, all right, to our switches, and we're going to diagram that a bit more dramatically and later on. Like I said, I'll wipe this out and we'll do this a bit better.
Sure.
This would actually go to probably an SVI, right? An SVI of the switch here, an SVI of the switch here, and we would normally use two separate VLANs to those two switches, just so that we would have some redundancy, if you will, in the VLANs. It makes it easier to manipulate traffic. Although, yes, you could use a single VLAN. There is no technical requirement for it. It is more of I would just say, a more efficient IO management of that traffic. And we'll get to a little bit later on also, because they are two separate VLANs. Yes, we are not recommending the use of an MLAG here, right? Or any type of multi-chassis ether channel, no matter, whichever vendor you wish to use. Okay?
I always say, and this goes back to my own design principles. And when, I was doing network engineering, it was use routing. Routing's fantastic. Just keep on using it.
Right.
Layer 3 is great.
The thing is that it's not anything antagonistic to the switch vendors. The idea is that each of them incorporate a series of proprietary extensions to their own purposes. And there's no way that we're going to be able to continuously provide a QE and a QA, right? A quality engineering and quality assurance that those particular elements of all of their beauty and value to that vendor's switch fabric management of that routed connection works efficiently against the way we would desire it to be. So therefore, we test things based upon what every switch vendor can apply in a cohesive manner as far as eBGP, OSPF, and static routing, which are the 3 protocols we do support.
And just to double down on that as well, it's not that Paul and I don't, have an appreciation. We understand, the different MLAG technologies that are out there. We understand the fooling and spanning tree. We understand configuration of the peer links and how it all works with the VPC. Like, we get it. We understand it. But Paul's very much right. I mean, and especially from just a configuration standpoint, it's much easier to use these layer 3 connectivity to your SVIs instead of having to like get into the complexities and additional configuration of doing MLAG. So keep it simple. We're big fans of keep it simple.
Correct. If we were to then draw in the edge nodes in here, let's see if I can draw on something that's going to be a different color slightly just for the moment here. So we would have, let's say, 2 virtual machine edge nodes. Each of them would have a VLAN for the adjacency communication to each of those 2 switches. So let's say 10 and 20. So there'd be a VLAN 10 and 20 on edge node 1 and a VLAN 10 and 20 on edge node 2. And there would be 4 uplinks. And then we can decide if we're going to run those in HA or if we're going to run those in ECMP. Obviously, with HA, though, we'd probably only be able to use 2 of those 4 uplinks anyway. But the issue being we would utilize the 2 edge nodes in a variety of circumstances, depending upon our needs and our desires and what services we wish to operate upon those as well, because we got some stateful functions that we can add to the edge node servicing where we're going to have to use HA for specific services because specific services don't allow routed out for them for a stateful means. Or we can use, let's say, stateful firewall, and we could still use an ECMP setup. But that's because there's so specific things that are going on behind the scenes that are automated in a way that allow for that to work. And you should be aware of how that's working, although you don't really have to do much to make it happen.
So let me highlight on something. So this has been a long roundabout way of getting back to what I was highlighting in here. And let's just, now that you've drawn this out, let's go back because you've drawn it out perfectly, but I want to highlight those components. So again, the edge node is also a transport node. We hit that just like ESXi servers or the NSX vSphere workloads that you have on the left-hand side there. And just like an ESXi server, it can connect to more than one transport zone. So listen to that, more than one transport zone. That means overlay and VLAN transport zones. But let me be very clear on this as well. A specific edge node can only be connected to one overlay transport zone, and depending upon the technology or topology, is connected to one or more VLAN transport zones. So just like in your drawing there, you have your NSX host, your edge host right there, connected to one overlay, but you have multiple links that are going up to those top of rack switches. So those are multiple VLAN back transport zones that are attached to that edge.
Well, technically they can be one or multiple. You can
one or
include,
multiple.
Yeah. I in my NSX on ACI lab, I actually use them as separate just for the pure sake of actually demonstrating the fact that you could separate them for whatever reason. And then, or you could make them as a combined one. There's no necessity to do either one in my particular circumstance, but there may be in others. You may want a rationale for crafting them in different ones, because remember, if they're in different ones, we're going to then have some unique aspect of how routed communication must occur between those different transport zones into and out of the physical fabric, as we would not be able to provide that in the virtual environment. So that may be an explicit reason why you may want that transport zone because of a different one, because of that rationale. And then back to, by the way, the edge here. Now we talk about the edge nodes. That's the virtual machine. So that's, I think we should go back, Andrew, right now and clarify nomenclature at this point.
Sure. So, real quick, though. So 6 Donuts actually did ask a question. I don't know if we're going to hit on this today. He goes, in another session, can you go over stateful gateway services and how to migrate to stateful gateways? Yes, we absolutely can. And Paul and I can plan a show around that. Obviously, stateful gateway services or anything's going to enact us creating an SR and all that good stuff. We can definitely talk about that at another show.
Right. Although migrating is probably going to be the better word, because it's not really an update or an upgrade, because you're going to have to probably craft a separate set of edges and then move your transpec over to it. But because there's an issue of just doing it on the actual nodes themselves, if you want to keep them running and then initiate now some stateful ones, you're going to have to do a little bit of maneuvering to make that happen, because it's not something you just do in place if you don't want disruption to occur to a greater extent. And we'll get to that in, like he said, another show. It'll have to be, because that is a little bit of a complex talk. Okay. All right. So let's get back to then the nomenclature aspect again. So we talk about there's vSphere clusters. And the reason we concern ourselves with vSphere clustering is because of the services we wish to leverage: DRS, HA, and of course, with DRS, you get VMotion, right? So we can VMotion workloads, right? And we can VMotion the edges. So the edge nodes. Let me rephrase that. And so what are the edge nodes? Those are the virtual machine form factor of the edge itself. There's two form factors: bare metal and virtual machines. Both of those are considered edge nodes. Now, here's the tricky part. We often just utilize for the edge itself, you'll just hear people say the tier 0 this, the tier 0 that, fix it a tier 1 this. And then people will sometimes not understand what we mean by tier 0 or edge nodes. Well, the tier 0 is the abstraction of the entire descriptive ideal of what is running the edge communication. That's the tier 0, and that is our gateway from the physical into the virtual. That's the tier 0, and that would encompass the edge nodes clusters. So that could be either bare metal or virtual machine form factor. You cannot mix the two in a single edge cluster. My NSX management can manage multiple bare metal clusters that are running tier 0s, and I can manage multiple edge node clusters that are VM form factor, that are also in a tier 0, but I cannot mix them in a singular edge node cluster.
I think that's an important thing. And just, actually, that was one of the notes that I had that I was going to talk about. Let me skip down to it. So one of the reasons why you would use a bare metal edge is because of the fact that it's basically, in terms of performance, it provides sub-second convergence, faster failover, and higher throughput at lower packet size. So, at low packet size. So like those are some of the reasons why you would use a bare metal versus a VM. And just real quick before we continue on, just two things. Number one, there was a question: why isn't stateful active possible in NSX Federation? I personally don't know the answer to that. And we would have to actually talk to the product owners on the Federation side to get an exact answer.
It's only for the fact that when we're managing Federation, remember that we're extending in a variety of different designs that we haven't really gotten into on whether or not that T0 is split across two sites, or it is a singular site with an active standby servicing on the other site, or it's part of, obviously, that's more the multi-site. I guess the Federation would be more along the line of we're managing how we're communicating the services from the global to the local management, and it's how the global would have to communicate that control plane configuration to each of those various instances. And it creates a little bit of an effort that must be coded appropriately in order for that to function in the form that you wish. So we remember when we're going to, since it's outside the scope of today, which is already mentioned, but I'll just kind of go into it for a brief second. The stateful functions that you would want to operate in an ECMP or an active-active. So we say active-active ECMP in the routed aspect here. Okay, obviously active-active could mean something entirely different for other things, but for routing, it means ECMP, essentially. You have to then utilize edge nodes in pairs, because there's going to be this failure domain that you're going to create, and then there's the idea of two edge nodes that actually pair up so that the stateful routing functions in a manner can be failed over to another one in the time of a failure within that edge node cluster. So in that edge node cluster, let's say you have 4 of them to keep them simple. Sure. 2 of them will pair up in a failure domain. One will be the active, one will be the standby instance, but all 4 nodes can actually send and receive the IO of that active-active ECMP communication, but only one is technically providing the filtering for a particular flow. So each of the particular flows will get sealed. I can't think of the right word at the moment. Or placed on a particular node at the time of its initiation of use. And then what will happen is as flows come in and out, there's this transparent communication that, and I say transparent because you don't actually see it, but there's a specific segment that gets created on the north and the south perimeter so that the edges, when something is received on the wrong node, it'll transit across that communication link and bring it to the proper one, because there's a note in the mapping table that says who's actually mapping and taking care of that IO communication flow. And then that one will actually then provide the stateful communication. And on the southbound, the same thing is the tier 0 or the tier 1 or the tier 0 DR receives it and then is going to send it to the appropriate ECMP communication. If it sends it to the wrong one, it will go, that the wrong one will actually send it to the right one on the south side of it so that it can transit north through the appropriate firewall rule table. So those are aspects of that. In Federation, it's obviously a bit of an extra effort to manipulate and manage that across federated instances. Although it would appear that you could do so in a more singular fashion per each of the instances, it still has to be managed from a global perspective to each of the instances. So there's a bit more of an effort there at the moment. So it's not something that's offered today.
You know what, and a good way of being able to look at it, and I can actually present really quickly, even though it doesn't have anything to do directly with Federation, is if I were to present this, just to kind of like, you know, put a visual to it, if you will. Am I sharing the right screen? Nope, wrong screen right there. Allow, and then let me bring this in. So this is kind of what Paul's talking about there. We're talking about the failure domains. Now, obviously, this isn't taking into consideration separation of sites and federation, things like that. But essentially, this, you know, having a tier 1 SR here and having, you know, multiple you know, failure domains in here of, you know, edge node 1, edge node 2, edge node 3, edge node 4, and then the active and the standby. This is active standby, but obviously you're talking about an active. But essentially what he's talking about, and this is what I kind of suspected, and Paul's getting into, is there's a mass amount of synchronization and how the traffic and the IO in an active situation that in Federation, there are probably some technical reasons I would imagine from a synchronization standpoint why it wasn't there or brought in. We can confirm with one of the product owners to get you a full answer. I don't finish, but definitely we'll get you some information on that.
It's going to come down to the RTEP. Because remember, when we transfer it over through that RTEP, we do have to hit a stateful firewall rule. I don't know how they would track that between the two sites in the way we do it today. So in other words, something would have to get added in some tiered fashion to allow for the RTEP to also be associated with possibly that simulated south and north barrier. I don't know. I'm only making a guess.
It's got to be something with the statefulness of it, for sure. Absolutely. And a real quick quote or note from Six Donuts. He says, "Thank you. This and the prior 2 sessions have been great. Thank you so much for tuning in. We love doing this for you all. So thank you so much for the compliment." All right, Paul, let's continue on.
Sure. Oh, that's my brother. So your brother has to now send a good accolade for us now too. So
excellent. And I don't finish that. Thanks for the info. I'm hoping that we gave you enough of an answer there.
All right, let's continue forward then. Okay, now I think we just want to clarify the final things of our discussion. So we talk about an edge cluster. Let's make certain that we're referring to the edge nodes themselves, okay, not the vSphere hosting the edge nodes, okay? So we're talking about the edge nodes. So we say edge cluster, we're talking about the cluster that's hosting the virtual machine form factor in our discussion, because we're not going to do bare metal here. All right, so unless we mention explicitly bare metal, always assume for the edge we're talking about virtual machine nodes for today. And I think that pretty much takes care of it, because we did the VLAN, we did the overlay, we got the vSphere clustering, we got the use of the DRS and HA capability of vSphere. So if we fail an edge node, it can actually come up. Or if a vSphere hosting an edge node fails, that edge node, we do have the option of bringing it up. Obviously, bringing it up somewhere else, we're going to have some issues with the adjacency and how that would align to the physical connection going in and out of a particular transport node that's hosting that edge node. So you got to make certain you realize that it's nice that we have it there, but then you also have to plan for how that would react in your particular topology and setup. So whether you're racking them in one rack, racking them in 2 racks, allowing failure or VMotion between the 2 racks because you want to have rack failure for your edge, those are all design considerations. So I'm only bringing them out there so I know that in your mind you may have already thought of that, and I'm just going to say, yes, those would be design considerations that we're not going to do today.
So one thing I think that, you know, people always have a difficulty with when I hear people that are new in NSX, and we hit it I think ad nauseum here is the VLAN back transport zone and the overlay transport zone and how it relates to the edges and the ESXi host, and they all become transport nodes. I think the other weird thing, and then you kind of talked about it, was how that tier 0 kind of like it overlays on top of all of those edge nodes. It's not, now you can only have one singular tier 0 for an edge. Let's just go ahead and point that out. But the fact that it almost like a logical concept of a router spread across the cluster. Do you want to dive a little bit deeper into that?
Right. So let's talk about that. So I don't know, maybe we should leave this here for the moment, and then I'll draw this over here, and then we can come back to it. So let's talk about, let's do this. Let's do something of a similar diagram at least. We'll just draw it out in a much more dramatic fashion. Okay. All right, and we're going to simply draw in mostly just the edge with some little workload domain. So it's obviously not to scale of how an environment would truly operate. So you would have your virtual machine edge nodes. So we actually, let's draw this. Let's do this. We would have what we would call our tier 0. Okay. So in our tier 0 is going to be made up of our virtual machine edge nodes. Okay. And we're going to draw out 2 of them here. Now, you have to recognize that the edge nodes themselves actually run 3 features. They run, and then we'll put this as the pink part here. We'll do this. They run the TEP. Okay. And they're also going to run our VLAN communication. So they're also going to run the VLAN segments for the upstream communication. We're drawing them as 2 because they will symbolize the 2 different VLANs that would interact with the upstream physical switches. So they're running the TEP, right? That's our TEP. And they're also going to run inside of it two distributed routed services plus an SR service at a bare minimum. They're also going to run the tier 1 and the tier 0 because they're going to run both of these tiering services. Now we're drawing this a little different than the design guide on purpose, just because we're drawing this out using the virtual machines. Because I think when we draw it out in the design, they show they typically draw this like this. They'll do the tier 0, and then they'll have the tier 1s.
Yep, correct. Yeah.
And unfortunately, to a newbie or someone else who's just looking at it for the first time, they're scratching their head trying to figure out what the heck that means. Yeah, because that doesn't make a lot of sense to them. All right, and I don't blame them. It's kind of a vicious circle, if you will. You know, where do you get on the wheel so you can understand it? Because it's like one of those things where you got to kind of read. I'm not saying to read all 400 pages of the guide, but you definitely got to read more than 50 to 100 pages at particular areas of the guide to probably really have a true concept of what that actual drawing means.
I mean, they could be looking up there and wondering what the heck that circle is and why you're circling 2 instead of a tier 0.
Right. So the tier 0 is an abstract concept that represents, let's say, the totality of the services that's actually here. So that's the actual entirety of the edge communication. And remember what it references also when I said before. It references the communication that's going into the physical fabric. Okay, so this is our physical router up here. Yep. So it's representing that. And it's also representing the fact that it's transiting the initial hop into the logical segment of our network virtualized environment of the overlay for NSX. So it's that first hop. So when communication comes into the T0, real quick, we're not doing a big trace flow thing through all of the different things because there's quite a handful of items that are actually involved in that hop. But it comes in through what we call an SR interface, and we'll get to that later on. But it's an interface that's managing the physical uplink connectivity into the physical switch, right? And that interface, as soon as it comes in through it then transits through a series of items within the tier 0 itself before it hits the tier 1. And then the tier 1, then from here, it's communicating to a host. But the point it actually has received, there's already resolution of where it's going to get destined to inside of that virtual environment because it's already done a lookup into the control plane of NSX and it's discovered where it needs to go. So all of this is just sort of a cursory idea of how the packet must transit through the environment. But in essence, it's already knowing exactly where it's going to encapsulate and send it to a remote TEP where that virtual machine that is destined for that original communication that came into the physical fabric, into the T0, through the T1, into a TEP, and then the TEP sends it to the destination host. And why is that important? Because notice what I just did. it got routed in its entirety on that edge.
Yeah.
So when it went to the other side, it was technically an L2 communication at that point.
It was already done. It did the routing.
It did the routing. So the only thing there was actually the source interface of the T1 of the distributed router component was the source MAC that was being sent to the destination MAC of the virtual machine in the encapsulated frame. In the outer frame, it's the source TAP to the destination TAP. And of course, it's MAC and IP addressing.
I think we actually talked about this about 2 or 3 weeks ago, where we actually went through and explained like the routing is done locally at we were referencing ESX host level and having a couple VMs on different VMs on the same host. And then we had an example, one on a different host, and showed, look, the routing is done locally on here. And then it's essentially completing the layer 2 hop, through encapsulation going to the other host. But it's the same thing on the edges. That's what we're highlighting here. It's like, it's the same concept overall.
Correct. What should be noted too is that when we reference these 3 little items here, I said this was a TAP and these were some VLAN values that were going to be used for the profile of communication for my uplinks. And these would be my TAP for the transport portion within the profile itself on the edge nodes. Recognize that those would be represented as also as DB port groups inside of the VDS, because we're going to transit that from the edge nodes into the VDS, and then the VDS uses its uplinks, its VMNICs, all right, or the DB uplinks as they're known inside of the vSphere or the vCenter interface. You can name them something else, but it's DB uplink 1, DB uplink 2,
sure.
which is odd. They use 1 as the initial one, and everything else is 0 for the initial one. So it's obviously Funsville there. But nevertheless, the DB port groups would be the actual the logical connections that the vSphere host participates in, transiting that communication in and out of the edge nodes. That's why I said when I skipped a lot of things, because we were just doing the logical concept here, and the physical traipsing of that concept would be a much more dramatic extension of connectivity ideals that would have to be transited through in order to actually make all that happen. But here's the beauty of all that. The only thing you're really managing is that initial adjacency that you have to make the connection, the routed values that you would permit to be advertised to the physical fabric, and the fact that you would have to assure yourself that what of the NSX virtualized environment do you wish to have advertised to the outside, and in what form? In other words, are they NATed, or are all those IP prefixes going to be done in their original sourced IP space? So those are the main things you have to do. Now there's a ton of other things you can do, but those are the things you would have to do in order to make it operate. And NSX technically takes care of the rest for much of any of the resolution. You just make certain that if you do those appropriately, NSX by default is actually pretty simple to set up, a fairly complex twisting of communication, or not twisting, but very complex arrangement of communication as it would appear. But it actually is fairly straightforward once you get the handle of what the abstractions mean and what they're doing, and realizing you're not doing a lot of it yourself. We'll get to more of why you're not doing that as we continue on.
And I think there's 2 points there that I want to point out. Number one, let's pull back what you just said earlier, because we haven't really talked about that, and I just want to do a little bit of a recap. So that distributed port groups and how it's controlling the VDS. In 4.0, we stopped doing the NSX VDS, or the NVDS it was called. So we no longer do that. And now we just control the VDS. I believe it started at VDS 7.0. And then whenever you make a segment, it shows up as an opaque group onto the distributed virtual switch inside vCenter. So you see it, and then you can attach those VMs to it. It used to be there was a separation between the NVDS and the physical interfaces that went to it. And, your typical distributed virtual switch that was in vCenter, now those have been combined. We don't do NVDS anymore. So that has been deprecated. Number 2, what I want to point out is, go ahead.
I want to make sure that we clarify something. We don't use the NVDS on the vSphere host, but the Edge virtual machine still use the exact same code base of that NVDS. And the reason is what they did is they paired up the code of how that NVDS was from the very beginning to be almost identical to the VDS. But because there was a bit of complexity initially in our initial forays of our NSXT flavor of NSX, right? Because we had T and we had V. The NVDS was separate because we had also a series of bare metals we had to put that NVDS on, and we had the edge virtual nodes we had to put that on, and then we also had to put that on the vSphere host. So it was simpler to just code that as a simpler singular model that might have some discrepancies for the VDS. And then as time went forward, we mapped them together in such a transparent fashion that the NVDS is now the VDS. The NVDS here is just a code base of such a similarity that you actually operate it as if it is the VDS, except it's only individually in each of these nodes, as well as your bare metal edge.
Gotcha. And then the other point I wanted to say is, look, the whole reason we're pointing all this out, and it might seem like there's a lot of complexity here, and there's a lot of, and you're right, to a certain degree, there is a lot of things that are happening. But the cool thing is when you do it and you configure it, it's super simple. The whole idea is we're actually breaking down these walls. We're opening up the the kimono, if you will, and revealing behind the curtain all the dirty details of how this stuff works, but it's super simple to configure, and that's the whole purpose, is so that you don't have to worry about all these little things and intricacies that are happening. But if you want to troubleshoot and you want to know how this all works, how the the sausage is made, how the donuts are made, we're showing you exactly how that's done.
Yep, as sloppy as I just did that right there, he is correct. Okay, so now what we showed you was, I said that the packet traipsed through this environment, as we noted, come here. And then we're going to talk a little bit about what happens during this intersection of communication here. And then, as I stated, it's actually going to get sourced from the interface here, all right, which technically then would be on the TEP, and then it would go to another TEP here. All right, and then it just goes right to the workload because it's at that point on that logical segment. So when its wrappings are removed by the TEP on the destination vSphere host transport node here at this point, it removes the wrapping, sees the underlying Ethernet frame, and then just looks to see where to deposit it on it. But again, there's some markings inside of that Geneve header that tells it that it's actually destined for a virtual machine on that host. So it's aware of that. And then it goes ahead and makes the appropriate move of that frame onto the appropriate logical segment. And it's picked up in a standard Ethernet ideal, so that again the virtual machines have no concept that they're actually operating in such a manner. The reverse traffic, though, and this is the interesting part, would actually then follow through sort of reversal in an asymmetric fashion of what we just happened here. The reverse traffic would actually come into the T1, go through the T0, go into the TEP. And then we're going to talk a little bit more about what that happens, but there's an actual interface here that we're going to talk about, all right, that's going to go through the T0's designated or distributed router service, but the specific element of that transits across to here, and then it'll exit out the SR interface once it hits the T0 here. Obviously, that's actually going through the TEP to the TAP, but it's a specific transit communication that's going to be used as it moves through here, because this system here is going to already know that it's going to leave and be routed out of the environment the moment it hits here, because of the fact that we have a distributed routed control plane of information, so that each of these hypervisors is aware of where to route it to another hypervisor in case this particular packet was going to ping pong through some east-west communication before it actually was to leave. But in order for this communication to, let's say, just do the TCP handshake, for instance, for the endpoint that was the source to the destination virtual machine, to do that SSL web sockets communication, the TCP handshake, just for that, we'd have a series of packets that would go back and forth between it before it would actually do its ping-ponging around internally and then offer its reply, if that's the way the app works.
I think what we'll have to do, Paul, one of these days for a show, and we'll talk about this, is, we've hinted so much and talked about the DR, the SR, and what it does. But I think it'll be really cool if we get a couple of hosts in the lab together. And what I'll do is I'll put everything together and we'll dive in and we'll actually show through command line the SR and the DR, and we'll show this packet and everything that's going on. We'll set up a couple of hosts and just do some basic communication, set up an underlay, and then we can simulate an enterprise network and show how everything actually comes together.
And I think also what we can do is use the visibility tool that you have at NSX. So you see how NSX provides visibility of that linkage of communication within its framework and understanding, because obviously the NSX visibility tool is only going to have an understanding of the virtual infrastructure and what is coming in and out of the physical infrastructure through into the virtual, but nothing of what actually happens on the leaf spine network, or if it's hitting some physical load balancer before it's coming into the virtual environment, or if we're using a virtual load balancer, we'd be able to see that in the visibility tool. Yep. Then we also have our old friend Bernie, now named Aeon. Okay, ARIA operations for networks. I don't know if they actually like that. I know the Bernie people hated Bernie at the beginning, but I guess they just got used to it because no one else was going to sit there and say vRealize Network Insight.
Don't worry. Nobody in chat's going to tell them. Nobody.
So with Aeon, or ARIA operations for network, it just seems like such a mouthful. All right, I'm just going to go with Aeon for our purposes here. Is essentially then going to provide us the other visibility tool, and I think, Andrew, would be really cool is that we line up those visibility tools with the CLI, and that we can actually show sort of a mapping between what the CLI is telling you and what the GUI is telling you for those tools.
Yeah, I love that idea, and I think that we're gonna have to put that together. I do have a quick question for you. So, we've actually blown through. We have 50 minutes that we went through, and I think that was fantastic. We only got through a few of my notes that I had, like holy cats. But I do have a question. So is there anything more that you wanted to hit upon this? Because there's one more topic that it kind of relates to it, and it's a hint. It's about the PNICs and uplink profiles and things like that. Did you want to hit on anything else before we wrap it up with that last subject?
No, I think we'll stay there because, as I stated, there's a couple of ideals that people should be aware of that makes this happen. As I mentioned, there's a T0 distributed router. So remember, that distributed router happens here, but there's no SR feature for it. The SR exists where we wish for the edge to provide the NSX to VXLAN, or excuse me, NSX to VLAN and to Geneve communication to occur. So that SR will occur at a specific centralized point. And that's an important perspective. So that SR, that services router interface, is going to occur in a specific centralized fashion. So that would exist here, but it's distributed so that we can utilize simple high performance rewrites of what is necessary to make that packet that packet properly managed and manipulated in an Ethernet format between its communication in the infrastructure. And then, of course, NSX control plane is managing and manipulating the control plane understanding so that the data plane operates efficiently, knows which taps to send data traffic to in the virtual infrastructure, as well as know that, oh, this thing's going to get routed and exited out of here. Better send it over to that T0. Yep. So those are things I think you should be aware of. There is, for the distributed router, there is a link that's used, and that uses a 169.254 address, so that when we talk about the DR sending it to the SR of the T0, that's a specific auto static, if you will, managed connection. So you don't do anything. It just, when you set it up, it just automatically goes ahead and pulls a couple of addresses from the 169.254 address space. We all know that's link local. It means those addresses are only local to it. So any other T0 instances you have, for instance, you have 10 others, doesn't matter. Each of them have their own and they operate on their own, as well as the T1. The T1 uses a 100.64 link specifically to interconnect those, because I'm sure people are wondering, how does that operate? Again, that's sort of a link static in an auto fashion, so that when we wish for information to be routed to and from it, and what IP domain space we want to be advertised, all of that is pushed through that particular link in the control plane for knowledge of what has to go into the OSPF, BGP, or static route table for the T0. All right. And that creates that link between them. Once again, you don't manage it other than it's set up automatically when you first set. So if you're saying, well, if I have 100.64 used somewhere else, that's fine. You can change it at the very beginning. There's a specific RFC that allocates that 100.64 for particular special use cases, such as this. So we leverage the use of it for that purpose. But if you don't like it, you do have the idea to change it, but you have to change it upon initial instantiation of the T1. If you don't, you'll have to scrub and redo.
Correct. Yes.
I think that, although that's a rather quick set of topics in a little format, that link you gave them for the DR guide, for the design guide, will explain that obviously a bit more profusely, but essentially I just gave you the highlights of it, and it'll make it very self-explanatory if you read it again.
Yes. And all this stuff is configurable. Oh, we have a good question. Hold on 1 second. We have a question. Edge nodes create some extra traffic in the DC. Why do we need edge nodes for north-south routing? Can't the tier 0, tier 1 DRs routers on the vSphere host communicate directly with data center switches? Oh, this gets into SR and DR. So why do we need an SR versus a DR? Let me take a little bit of a stab at this. It's mainly for the stateful services. That's like routing, NATing, any kind of thing like that, firewalling of some sort. Remember that you have to be able to keep track of the connection that goes in and out. The DR is great from a distributed standpoint because it's in every single one of the hosts, and you can have, let's say, that gateway distributed across all the different hosts. It can do the local routing if it has multiple segments attached to the tier 1. It takes care of all that in a nature that all of the different hosts can participate. But let's go from a stateful standpoint. If we try to put stateful services in the DR and you had traffic going out one host and then it hopped over to another host and came in, it would not be stateful in that case. And when the return traffic comes out, so we need an SR area that we can actually have, or edge nodes that eventually, if they have stateful services, instantiate a stateful or an SR tier 1 and an SR tier 0 to keep track of those connections. Paul, would you like to add even more onto it?
Well, there is a manner of doing what he wants to do, although we would not call it using the DR and the SR. That would be our EVPN. We would actually be able to provide something of a similar nature with EVPN, and there's a value to doing so. But that is a completely different use case, not really what I'm sure the question was targeted for. I want to craft a simpler means of connecting my workloads to the external space without going through a centralized routed plane for my north, south, and east, west. So the problem also would be is, remember, I'd have to be running eBGP. Let's just assume you could even do it. It's not feasible. It isn't logically plausible to do. But let's just assume you would want to do it. It wouldn't even be operationally feasible to do because you would have all of these eBGP connections you'd have to have from every vSphere host.
Every host.
North, south. So, I mean, assuming you could even do it, which you couldn't. But let's just assume you could. The operational side of that story would just be astronomically insane.
You would have 100 ESXi hosts that would have to have 100 BGP connections to a neighbor relationship to your all the different upstream switches, and like, look, if they're going to different racks and different upstream switches and different layer 3s, it would never work that way. That's why you have to have a centralized area for your routing policy, for your stateful policies. That's why it's actually done.
Right. And to centralize it in an efficient manner as we have, you have to, when you craft anything, any type of framework of any ideal, and in networking, before you would actually begin to put code to paper on something, you must go about what is the best way to do something, and then what is the more efficient way that it can be scaled and managed. And then there's a series of about 10,000 other things. We only touched on the first two just because those two alone would say, I'm not going to be able to do BGP from every host. Just when you look at it from those two, just those first two items alone. And there's, like I said, 1,000 other things I'm sure you could easily come up, and you might even think the first two I pick aren't even the best of the two. Nevertheless, the issue being is that I want to be able to create an efficient manner, high performance communication, and I'd be able to minutely manage how that high performance communication manages due to offloads and other things that I can prescribe and use from the vendors of the NICs and the hosts themselves that would actually be hosting these services. And I want to be able to scale it operationally efficiently. So I'll leverage then the ECMP of the routing protocols. And from those two perspectives, you begin to see that it's probably easier to do this because in a north-south communication, in today's world, and that's the third thing I guess we should consider, or maybe even first, and that is north-south communication in the data center today is less than, in almost all circumstances, less than now even almost 5% in most of our customer environment. When we first started this back in 2012, 2013, 2014, the original flavor of NSX data center for vSphere, it was somewhere in the realm of 70-30, 80-20. Yep. Today, it is almost 90 to 95 percent east-west, 5% north-south. So you could see that I really don't need, there's no critical IO value that I'm garnering by providing this operationally inefficient manner of communicating my north-south traffic, even if I could just do it from a specific set per every host in or for every row, or excuse me, every rack, and do a couple of hosts in every rack. There really be no value other than the fact that I might just want rack failure for my edges that are centralized, but there'd be no value for doing it in symmetry that the original question was framed as. There's no perspective value there.
Yeah, I mean, and look, like just to go back to that question, like, can't the tier 0, tier 1 DR routers on the vSphere host communicate directly with the data center switches? I mean, theoretically, obviously they are, because they have interfaces that are coming in, and that's what we're doing for the Geneva tunneling and sending it off to different hosts. They are communicating, but I think what you mean is communicating in a sense of a stateful manner. Like I said, we've been talking about, routing protocols or a gateway firewall or things like that. Because remember, and let me be very clear on this too, because you might be thinking, well, Andrew, you said about, the distributed and stateful, we have distributed firewall. How the heck is that working? Well, think about it from this standpoint. You have one NIC going to your VM and a VNIC going to another VM on another host. There's always the same in and out going into it. So it's not, while you have distributed firewall where the rules are being distributed out and applied to each of those hosts and their VNICs appropriately based on, could be scoping or whatever it is, or if it's DFW policy, the in and out to the VM is always going to be going through that VNIC. So it's in a stateful manner. Whereas with distributed routing and switching, it like Paul was saying, 100 BGP connections would be just absolutely insane. And the mechanics of it just doesn't make any kind of sense from an operational standpoint.
Right. And we'd have to also not go into the actual logical structure of how that would actually even occur, because you'd have routing issues. You'd have to make sure of routing loops. You'd have to make certain of the fact that you would have to manage on the physical switch fabric side all of those EVGP adjacencies. It just isn't. It would make no sense whatsoever, because you would run into all kind of routing restrictions anyway, where you would end up garnering almost no efficiency out of it in the first place. So,
I guess, Manuel, what I would ask, Emmanuel, is, what would be the reason why you would want to do that? Because I know that we're conditioned from the sense of like traditional networking, where we do have our layer 3 interfaces and our SVIs. They usually go to something where we try to do traffic steering in some way, shape, or form, maybe even PBR. But as we've kind of shown with traffic flows and how things have evolved, and what Paul's stated with the SRs and the DRs and traffic patterns, it doesn't really make sense to even do that. But I would love to hear exactly why you're thinking that way, or was it just a pure question of you wanted to understand better why?
Right. Like, we get into a topic at some point later, which I'm sure we'll do, and we keep continuing these on in our discussions. We'll get into some EVPN design ideals, and you'll start to see, well, there is a rationale for doing that from an EVPN perspective,
Sure.
because there would be some direct advantages of not having all of your communication going into the edges, so a virtual machine can communicate to through a layer 3 connection. Where it has to route out and then go to a VLAN back communication to a particular bare metal system. We could plausibly use an EVPN style connection directly to it off of a tap of a host. So therefore it could be a bit more exacting on that communication. Although we'd have to, our setup for EVPN would have a control plane that would not be the same as far as how control plane knowledge is actually transited between the environment and the hosts themselves, whereas a data plane can operate in one of a couple of different ways. One of them would be that more direct fashion I just mentioned. Another one, of course, would be through an inline mode inside of the edges. So
yeah, and I think Paul, what you're kind of referring to there is like we've talked about this before. There were some specific use cases in EVPN that were designed for service providers, specifically the mobile network and the phone network, and we talked about that, inline mode versus route server mode. We had a very in-depth conversation with a couple of the product owners on that, and we intend to do a show live discussing those different use cases in the EVPN solution that we provide. So, and Manuel just responded. He said that it was just to understand it better.
Now, you said you want to try and cover something else because we're kind of running a little long today. So
I think, we ran long. We're already at an hour and 3, and you know how I like to try to keep it on that time frame. So I think, honestly, next time what I would love to do is talk about, just for the crowd a little bit more, some of the uplink profiles, some of the things that apply to, because we talked ad nauseum about, the different transport zones and the different ways that we connect to it. But we haven't really talked about the physical NICs. We haven't talked about the abstraction between a PNIC and the uplink profiles that we have. And we haven't talked about the load balancing of it and what we recommend on how we do load balancing. And do we even recommend doing a lag to the switch, which, by the way, we don't. And it's in the design guide. So we can talk about those subjects real quick. Oh, go ahead, Paul.
Well, remember, MLAG, we don't like for the routed. Lags, in other words, if these two connect, if this was two separate links here just for the singular link and two separate links, there would be reasons why you might be able to do that. But even then, sure. I think I would agree with what you said. There's no value from our perspective. So we would, normally it's the MLAG is the one that people consider. And I don't know if you would even do a lag on the edge. You might do it to a vSphere host. And on a vSphere host, there is some advantages to doing lag. And there is some advantage to an MLAG. And although we don't go around telling customers use your MLAGs, they're invariably going to do so. So we just assume that from that perspective. But from a support issue here, you're going to start running into a problem where if it is the MLAG servicing, because we can't find anything else, and invariably this has happened. So I want to make sure customers are aware of this. Again, it's not to target the vendor itself. It just may be some incoherence between the use of some feature in that proprietary setup of that MLAG that just isn't conducive to whatever particular transiting was required between the routed segments, or something did not get resolved appropriately on the physical side versus the virtual, because usually it's not going to be a resolution issue of our side of it, because our side, the resolution is pretty much, I wouldn't say idiot proof, but it is fairly simplified, where that's usually not going to be the problem. The problem is usually going to be something of that negotiation into the physical across that MLAG. And then you start running into all kinds of tangents that go into, well, they use this feature on that MLAG because this feature allows for some crosstalk communication, and there's a specified link that provides this and all this other stuff. And when you start doing that, you can obviously see why we can't go off and say, stamp our approval. It's going to work on, the use of VLT from Dell, or the use of VPC from Cisco, or the use of, I think we just call it MLAG at Arista. All right. Yeah. So, all right. So, we can't stamp our approval because there's no way for us to track each of the features that they're going to add into their setup, because again, there's no standard.
Yep, absolutely. Well, Paul, let me do the wrap up here. And I want to thank you again for doing this. We have one more next week, and then we're going to have a set of shows that are coming up, which, by the way, I'm going to let everyone know what those shows are. But next week, Paul and I are going to be back on a brand new topic of NSX networking. Thank you, Paul, so much. I appreciate it.
Well, thank you, Andrew. As usual, it was fun. It went by way too fast, and that's a good thing, I suppose. That means you're having fun, and hopefully the folks that are watching are doing so too.
Absolutely. Be right back. Stay on the line here. Ladies and gentlemen, thank you so much for joining. Now, by the way, something brand new. So I put it in the chat here on YouTube and on Twitch. It is our brand new area that we have, that we list all the shows that are going to be live and the topics. Now, remember, times and topics and things are subject to change. Last minute, I might update it. Actually, the show for next week, we're probably going to update what the topic is, just a fair warning. But then the week after that, we're going to be talking about advanced load balancer. We're going to have Pankaj on, and it's fantastic gentleman, has a lot of information, a lot of knowledge. So I'm very excited for you to hear all about ALB and load balancing. So if you are a fan of load balancing, I assure you it's going to be a great show. Come on to be able to see that. And then the week after that, we're going to talk with the customer. We're going to talk with Benny from Swisscom, and he's going to give us the service provider mindset of how they use NSX and what they did in their environment. So we've been focusing a lot on the enterprise, but we're going to have all about the service provider. So new shows are going to be put up there. I'm so excited that you all joined. Thank you for all the questions, and we will see you next week on the VMware Networking and Security live stream. See ya.